Okay, in the second and probably quite short part of this final part of this eighth lecture, I'm going to just finish on the evidence for superconductivity and introduce what is BCS theory. So, in a sense, uh, what is our best guess at the answer? Okay. So we've dealt with resistivity, we've dealt with the Meissner effect, we've looked at some of the thermodynamic relationships around heat capacity and entropy. What about optical absorption? Okay, well, as I said, so um, next, in the second half of term, you look at electrical and optical properties with Martin, and there you'll be looking at the behavior of metals and normal metals, so materials that actually have a resistance. It's quite interesting to think what would be the behavior of a metal that had zero resistance. Okay, that's actually potentially could behave quite strangely. But actually, the optical absorption of superconductors is not that strange. Okay, so certainly at optical frequencies, at light frequencies, a superconducting material and a normal material, they behave exactly the same. So there seems to be no special difference of the superconducting state. That's a little bit odd. That's not what we'd expect from a kind of perfect conductor. However, the important information occurs when we look at microwave frequencies, and it really wasn't possible to make good microwave sources, I think, until after um, sort of quite late on. But a lot of sort of work around radar and stuff sort of helped. But um, so these were experiments that were done sort of post-war. Okay, they're quite difficult experiments to do. But what it was found was that at microwave uh, frequencies, the superconducting state can be transparent. Okay, so if you take a thin film of a superconductor, the microwaves could pass through. But that it, when you increase the energy of the microwaves, you hit a critical frequency at which you get absorption. Okay, so the material will now absorb. Okay. Um, you could do this in other ways, make little cavities within a superconducting material, look at what happens to the microwaves. But essentially, they're absorbed below a critical frequency. Sorry, below critical frequency, they are not absorbed. Above a critical frequency, they are. This is quite curious behavior, and we've seen something sort of similar to that before, not the microwave regime. We've seen it for kind of uh, sort of optical effects. So, this is sort of resonance of a sort of a semiconductor. Okay, so in that case, we've got a gap. Okay, and if we shine light on a material and it's less than the gap, it won't be absorbed. And if it's greater than the gap, it can cause excitations in the carriers and it can be absorbed. Okay, so this tends to suggest that the superconducting state, although it's a metal, has an energy gap at the Fermi energy. Now, because this is in the microwave regime, not the optical regime, we're not talking optical means the order of a few electron volts, but if it's microwave transitions, this means we must be working in the micro EV regime. So these are very, very, very small gaps. Okay, that kind of fits in with what we said about the heat capacity and thermal energy and things. So we know these are really small, potentially very, very small gap. There's one other thing that's very different to semiconductors. So in semiconductors, you don't expect the gap. The gap of diamond doesn't change as you change the temperature, not in any appreciably measurable way. But actually, what's found here is the gap gets smaller as we approach TC, and at TC the gap is zero. We've gone back to being a metal where there's no gap at the Fermi energy. Now, these experiments were absolutely critical, I think, in guiding the theoretical approaches, okay, because this gave people the idea of what to look for in a theory. So let's just summarize where we've got to with the evidence. We know this is a universal mechanism, okay? It's very common, it happens in lots of materials, so there's nothing exotic about this. We know that phonons play a key role because the isotope effect tells us. We know there's a new excitation mechanism in the superconducting state because we get an exponential rise in the heat capacity. And we also know that the superconducting state is more ordered. We have evidence for a gap in the electronic density of states at the Fermi energy, and that gap gets smaller as we approach the critical temperature. Now, when owners first measured superconductivity in 1911, there wasn't the theoretical framework to begin to attack such a problem. Okay, and this was a really open question for a long time. Okay, the first serious attempt to try to explain the phenomena of superconductivity came by the London brothers, Fritz and Heinz London, in 1934, 1935. Okay, and what they did was they found ways of modifying Maxwell's equations in such a way that it would explain the Meissner effect. Okay, so it's interesting story in that Fritz and Heinz London were born in Germany. Fritz London was professor of physics at the University of Berlin, but they were Jewish, and when the Nazi Party published when they passed the 1933 racial laws, he lost his job, and the two brothers came to Oxford and they came to work in the physics department, the Clarendon laboratory, and that's where they did their work on developing the London equations. Fritz London, after the war, he took American citizenship and became a professor at Duke University. Heinz London took British citizenship and actually moved to the University of Bristol. And they went on to do, particularly Fritz London, did a huge amount of extra work in understanding magnetic properties of materials and lots of different contributions. Okay, so this is an extract from the header of the paper that they published about the London equations. It was in one of the Royal Society journals. And interestingly, you notice here the electromagnetic equations of the supraconductor. Okay, originally superconductivity was known as supraconductivity. I'm not quite sure when the change in name comes past. Okay, so this was the London equations, and they were very successful and they're very useful in describing certain properties of superconductors. But they were based on purely making an ansatz. Okay, so they took Maxwell's equations and then they said, if we assume this to be true, and they provided no basis for it, then we can show how we can derive the Meissner effect. Okay, and this perhaps represents a sort of a different picture of how to do physics. So you can have atomistic pictures. So you can start from, say, quantum mechanics or Newton's laws and very fundamental physics, and you can build up an atomistic picture of what's happening in materials. Or you can be driven by phenomena, what's sometimes known as phenomenology. So you can try and come up with a set of equations that describe the properties of a material without thinking about atomistically what the origin of the effect is. So to give you an example, so for centuries people have come up with thermodynamics way before any evidence for atoms existed. Okay, so that required you to have concepts such as internal energy and heat capacity and temperature and entropy. But it was only when sort of quantum mechanics came along and people had an atomistic understanding that we were able to develop statistical mechanics, and we were able to show where things like entropy, where the internal energy is stored, what is the result of heat capacity. Okay, but that doesn't change the equations of thermodynamics. And in many cases, the equations of thermodynamics are more useful from statistical mechanics because, to do statistical mechanics, you might have to work very hard thinking about all the particles in my simulation and what's going on. Whereas the thermodynamics might be more useful. They're just macroscopic quantities that you can work with. Okay. So the next major development was the Landau-Ginzburg model in 1950. Landau and Ginzburg, two Russian physicists, came up with, again, a phenomenological model of superconductivity that was found to be incredibly powerful for understanding a lot of the the properties of materials, superconducting materials. So this is both the Landau-Ginzburg model and, to a lesser extent, the London equations are still used. Okay, they're not atomistic models. They don't provide an explanation of where things come from, but they're able to describe a lot of the properties of a superconductor, and they're quite easy to work with. So they have a lot of power. The first atomistic theory was that of Bardeen, Cooper, and Schrieffer in 1957. And, I think this kind of stands with, say, the development of Maxwell's equations in the 19th century. This was one of the major achievements of 20th century physics, and this is an atomistic theory. So this can explain from fundamental quantum mechanics and the behavior of the atoms where superconductivity comes from. The equations are not easy. They're not easy to work with, even with large computers, and people often work with approximations to them. One of the things that was nice is after the BCS model was developed, people realized that you can make some approximations to it and arrive at both the Landau-Ginzburg model, and if you make even stronger approximations, you can get the London equations. So both of these earlier models capture elements of the truth in certain limiting cases. Okay, so that's why they're actually quite useful to work with. So we're going to talk about some of the aspects of the BCS theory, and then we will look briefly at Landau-Ginzburg and the London equations and show how we can use those to predict some of the properties of superconductors. Just to mention some, all of these people, bar the London brothers, won the Nobel Prize. Landau did, Ginzburg did, Cooper and Schrieffer did, and Bardeen won the Nobel Prize twice because, as well as the BCS theory, he was also responsible for developing the transistor. So that earned him a separate Nobel Prize, in a person to win 2 Nobel Prizes in physics. So I'm going to end just by giving you a flavor of what is involved in the BCS theory. How have we got this completely different phenomena that is not like how we expect metals to behave at room temperature? What is it that's happening in the material? And this is it. BCS predicts the following, that electrons can lower their energy by pairing up. Okay, and we call these pairs of electrons Cooper pairs, after the C in BCS. And they pair up so that each electron has a spin up and a spin down. Okay, so the 2 electrons, a spin up electron and a spin down electron. And that pair of electrons is the charge carrier. They move together throughout the material. Now recall from quantum mechanics, we can classify fundamental particles into fermions and bosons. Fermions had half integer spin, and bosons had integer spin. So bosons were photons, or phonons are bosons. Helium-3 is a fermion. I think helium-4 is a boson. Okay, just depends on the spin of the particle. Electrons are obviously fermions. So electrons have to obey the Pauli exclusion principle. Okay, they all have to have a different set of quantum numbers. Bosons don't. I mean, photons can all sit in the same quantum state. That's fine. There's no Pauli exclusion principle for bosons. Now, when you bring 2 particles together, the net spin of the Cooper pair is 0. So a Cooper pair is what we would call a composite boson. It's not a fundamental particle, so it's not actually a boson. It's what we would call a composite boson. And so if you like, Um, we know that bosons can all occupy the same quantum state. So what can happen when the material goes into the superconducting state, all of the Cooper pairs decide to go and occupy the same electronic state. Okay, very different to how fermions behave. Now, the final thing is that it takes energy to break a Cooper pair apart. So at low temperatures, these Cooper pairs travel through the material, and the scattering events do not have enough energy to break them apart. There is a gap in the electronic density of states. Okay. Now, these three things are pretty crazy. It took people a long time and a lot of experimental evidence to come up with these three things. As a start, I mean, it really does sound odd, because surely two electrons are negatively charged. Why would they want to pair up? Okay, surely they want to get as far away from each other as possible. So what could possibly create an attractive force between two electrons? And that's the thought I'm going to leave you with, and that's where we'll pick up in the third lecture by explaining how it can be that in the superconducting state, pairs of electrons can actually experience an attractive force.